This is the first of 3 videos where we'll be doing applications of vectors. There's different types, so I've broken them up into different videos. This video is dedicated to applications that are going to require the use of parallelogram rule. We use parallelogram rule when we have 2 separate forces pulling on a single object from like the same location. The following properties of parallelograms are helpful when studying vectors. It's been a while since we've had geometry and really talked about parallelograms, so let's review some of the rules for parallelograms. A parallelogram is a quadrilateral whose opposite sides are parallel. The opposite sides and opposite angles of a parallelogram are equal, and adjacent angles of a parallelogram are supplementary. I think that's definitely the one that we tend to forget the most. The adjacent angles are supplementary. The diagonals of a parallelogram bisect each other, but do not necessarily bisect the angles of the parallelogram. So don't assume that. You're going to be tempted to think that the diagonal cuts that angle in half, and that is not the case. 2 forces of 19 and 32 newtons act at a point in the plane. An angle of 118 degrees is formed between the 2 forces. We want to find the magnitude of the resultant force, and we'll round to the nearest hundredth. Similar to our trigonometry application problems, a good diagram is key. So I have 2 vectors acting on a force. And since these forces are different numbers, we're going to have the length of the vectors reflect the size of the number. So first one's 19. And just to make my life easier, why not make one of them perfectly horizontal? So here we go, 19. And here's the point in the plane that the forces are acting on. And then I have another vector. Let me make this a little straighter. I have another vector, 32 newtons, but the angle in between these two is 118 degrees. So when I draw in this second vector, it's going to be back here. It's going to have a length magnitude of 32. So here's where we do parallelogram rule. We're creating a parallelogram by making additional vectors. So this one's going to be 19 in length, so it should be the same length and the same direction. And then we'll have another one representing the 32. And I do my best to try to make them accurate. It's going to make me feel more confident when I'm actually doing the problem. So here we go. And then parallelogram rule says that the resultant is going to be the diagonal. So what we're looking for is this right here. Opposite sides are equal in a parallelogram. So this one's 19, this one's going to be 32. We also know from our second property, fact that we just reviewed, is that adjacent angles in a parallelogram are supplementary. So we have this angle of 118 right here. So that means I can go either angle to the left or to the right, and it's going to be supplementary. I think I'm just going to choose the one to the right. I guess we could label them both if you wanted to. And that's all the information we were given, but that should be all the information we need. I'm going to draw a breakout triangle. I'm going to take this triangle right here. Trying to find this side x. My bottom's 19, my right side's 32, and this angle is 62 degrees. Three sides of a triangle and one angle, that tells us law of cosines. Using law of cosines, we're going to get x squared is equal to 19 squared plus 32 squared minus 2 times 19 times 32 times cosine of 62 degrees. And then x is, of course, the square root of all that. So I would type it all in my calculator at one time, that just x equals the square root of all this stuff, because we don't want to round more than we have to. So if we plug it in all at once, we'll only be rounding a single time. We get x to be equal to, rounding to the nearest hundredth, 28.53, and our unit is newtons. And with these examples with parallelogram rule, really it's the same thing every single time. The key is to get a good picture, then you're going to do your breakout triangle, you're going to use the fact that opposite sides are equal, you're going to use the fact that adjacent angles are supplementary, that'll give you your breakout triangle, and then typically we are using law of cosines to finish up the problem. Let's try another one. This next example is going to involve the equilibrium. So we've talked about in previous sections methods for finding the resultant of two vectors. Sometimes it is necessary to find a vector that will counterbalance the resultant vector. This opposite vector is called the equilibrium. The equilibrium of vector u is the opposite of vector u. So kind of like how animals that jump have really long tails to keep them balanced, it's just the counterbalance. That's all the equilibrium vector is. So to find the equilibrium, we're going to have to find the resultant vector first. It's going to have the same magnitude, because we know that the magnitude of a vector and the opposite vector are equal to each other. And then when we find the direction, we just need it to be going in the opposite direction of our resultant vector. So once we get our angle for our resultant vector, we'll simply add 180 degrees, and that'll have it going in the opposite direction. Two rescue vessels are pulling a broken down motorboat towards a boathouse with forces of 840 pounds and 960 pounds. The angle between the two forces is 24.5 degrees. We want to find the direction and magnitude of the equilibrium. We'll round to the nearest hundredth. As always, a good picture is key. So here's my broken down boat. My first vector is pulling with a force of 840 pounds, and then my second vector, 960 pounds, just a little longer, and the angle in between them is 24.5 degrees. Now it's time to create our parallelogram. By creating the two sides that are going to be equal to the vectors that we have. You can draw them in solid. I like to dot them just so that I know that these are like the new sides and not the original vectors I started with. We're looking first for the resultant vector, which is going to be the diagonal of this parallelogram. But we also need to use the fact that our adjacent angles on the inside are equal are supplementary to each other, so that creates this angle 155.5 degrees. So I'm going to focus, right, solving this triangle. So I'll make my breakout triangle to the side. Looking for our bottom side X. Once again, we have three sides of a triangle and one angle. That tells us that we need to use law of cosines. So x squared is going to be equal to, I think I'm just going to write x equals the square root, so I don't have to rewrite it this time. So x equals the square root of 840 squared plus 960 squared minus 2 times 840 times 960 times cosine of 155.5 degrees. And we'll just plug that into our calculator all at once. Rounding to the nearest hundredth, we get x to be 1,759.20, and our unit is pounds. That's the magnitude of our resultant vector, but that will also be the magnitude of our equilibrium because it's just the opposite vector, and opposite vectors have equal magnitude. Now we need to find the direction. So we need to find the angle inside of our triangle, and we want the angle next to the boat, so I'm looking for this angle alpha here. Well, since I know this bottom side now, you could use law of cosines if you wanted to, but now I have a known pair because I have the x and then the angle across from it, so we could switch to law of sines. Sine alpha over 960 is equal to sine of 155.5 over 1,759.20. We'll cross multiply. Divide by the 1759, so sine of alpha is going to be equal to 960 sine of 155.5 divided by 1,759.20. And then to get our alpha, we need to do sine inverse of that fraction. Plugging that into our calculator and rounding to the nearest hundredth, we get alpha to be 13.80 degrees. But remember, we want the equilibrium. So we're going to add 180 degrees to get the direction for that equilibrium. We end up with a direction of 193.08 degrees.